Mrs. Kate at the Library of Whispers, and today we're going to take a look at one of my Voyage Through the Universe books. This is a set of books all about space and the universe, and this one is called Cosmic Mysteries. Now, I've not looked through this book yet, so I'm not quite sure satisfactory explanation of what happened. Practically all that can be said for certain is that the event of March the 5th was a pulse of gamma rays, the most energetic form of electromagnetic radiation, with wavelengths shorter than the radius of an atom. Gamma rays, which are undetectable from the ground because they cannot penetrate Earth's atmosphere, course through the universe from many different sources, constituting part of the omnipresent background radiation of the cosmos. During the 12 years prior to the 1979 event, scientists found that gamma rays also come in brief, high-intensity bursts that are many times more powerful than the background level. The discovery was an accidental result of the United States' efforts to monitor the Soviet Union's compliance with the Atmospheric Nuclear Test Ban Treaty of 1963. Since short bursts of gamma rays are an unmistakable characteristic of nuclear explosions, the US Department of Defense launched 4 Vela satellites equipped with instruments designed to pick up gamma radiation. But when the Velas first began to register gamma ray pulses in 1967, the data triggered more confusion than consternation. The signals did not match those that had been produced by previous nuclear tests, nor did they seem to be coming from anywhere near Earth. The findings were so unexpected that physicists did not even report them in the scientific journals until 1973, when a group led by Ray Klebesedel of the Los Alamos Scientific Laboratory in New Mexico, renamed the Los Alamos National Laboratory in 1981, finally announced the existence of gamma ray bursts of cosmic origin. Although no specific sources could be identified, theorists believed they could explain what the sources were. When a dying star explodes as a supernova, its core collapses to form a rapidly spinning object composed almost entirely of neutrons, packed together so densely that a teaspoonful of the material would weigh nearly 1 billion tons. If less dense matter, perhaps from a companion star, were to fall toward the surface of such a neutron star, it would collect, concentrate, and then fuse under the tremendous pressure, producing a thermonuclear explosion that would release a brief but potent surge of gamma radiation. Between 1967 and the late 1970s, more than 80 separate bursts were detected, all of which fell within a range of intensities consistent with this sort of process. The event of March the 5th, 1979, however, broke the mould in resounding fashion. To begin with, the recorded pulse was at least 10 times more powerful than the largest previous burst. It reached maximum strength in less than a millisecond, hundreds of times faster than normal, and exhibited a decidedly unfamiliar decay pattern of rhythmic pulses at 8-second intervals, entirely unlike the irregular static of most fading bursts. But its most surprising feature was its apparent source. The standard theory of burst generation rested on the assumption that bursts originate somewhere within the Milky Way, Earth's home galaxy. To pinpoint the March the 5th burst, an international team of physicists at Goddard and Los Alamos when something ceases to be mysterious, writes theoretical physicist Freeman Dyson of Princeton's Institute for Advanced Study. It ceases to be of absorbing concern to scientists. Almost all the things scientists think and dream about are mysterious. Often strange objects or signals picked up in routine scannings of the sky represent no more than slight variations on well-understood phenomena, necessitating only minor tinkering with theory. At other times, as in the case of the March the 5th event, observations are so baffling that theorists must start virtually from scratch to develop suitable explanations. Intriguing conundrums also originate on the theorist's blackboard, spinning entire universes out of physics equations and quantum mechanical proofs. The deep thinkers of celestial science continually send observers scrambling to their telescopes and laboratories in search of concrete evidence to confirm or refute the latest theoretical constructs. Whatever the nature of the detective work, tidy solutions are never guaranteed. Specific issues tend to divide scientists into opposing camps, each arguing for the primacy of a particular hypothesis or the significance of a particular detection. The disagreements sometimes become heated and may even endure for decades before new findings change the dynamics of the debate or occasionally settle the matter once and for all. Much of the time, on scales grand and small, the universe has simply refused to reveal its secrets, leaving theories unproved and observations unexplained. The mysteries confronting astronomers in the late 20th century range from subtle details of nearby phenomena to cosmic riddles in the deepest reaches of time and space. The familiar neighbourhood of the solar system remains a jigsaw puzzle with a number of missing pieces, and there are many strange doings still to explain among the Milky Way's panoply of stars. Farther afield, whole galaxies and collections of galaxies behave in ways that conflict with the accepted models for the evolution of the universe, and a host of exotic items and mind-bending possibilities, from quasars and black holes to time travel and multiple universes, lure scientists onwards in the search for answers. Okay, so let's have a read of this. The plunge into chaos. For centuries, scientists were sure that forecasting the behaviour of the weather, ocean currents, and other fickle-seeming phenomena would someday be possible, but during the 1960s, man chaos is not disorderly, sometimes out of turbulence and underlying order. Spontaneously emerges, a wave rolls unchanged over thousands of kilometres of ocean, or in what are perhaps nature's most spectacular shows of order in chaos, great storms such as those on Jupiter, Saturn and Neptune whirl undisturbed through seething planetary atmospheres, a mystery that scientists are only just beginning to unravel. Here is Jupiter and the Great Red Spot. Okay, let's have a look a little bit further. So this is called Pluto's Wild Streak. Nothing so epitomises order in nature as the planet's motions about the sun. Yet, even within this clockwork-like realm, scientists have detected intimations of chaos. Secreted in Pluto's orbit are the seeds of long-term unpredictability. Orbital analysis, projecting only a few tens of millions of years ahead, cannot pinpoint the planet's position. Their difficulty does not stem from any violation of Newtonian physics, rather the planet's sensitivity to the conditions dictating its orbit at any moment is so extreme that even infinitesimal errors in measuring those conditions result in wildly different predictive calculations. The discoveries of this planetary chaos were Massachusetts Institute of Technology physicists Jack Wisdom and Gerald Sussman, whose suspicions were aroused by Pluto's oddly tilted, elongated orbit. Right, let's see what else we have. The case for Planet X. For more than half a century, and with varying degrees of intensity, some astronomers have proposed the existence of a 10th planet, known as Planet X. The unseen world is invoked to explain certain anomalies in the behaviour of Uranus, whose calculated orbit works for one circuit but not the next, and Neptune, whose predicted positions are noticeably in error after several years. Planet X, if it exists, might also explain the odd orbital dynamics of Neptune's moons, Triton and Nereid, and the unexpected size and makeup of Pluto, which is so much smaller and rockier than its huge gaseous neighbours. The hunt for Planet X, based on calculations of its presumed mass and orbit, requires painstaking searches of designated patches of sky. In 1846 and again in 1930, such efforts paid off in the discoveries of Neptune and Pluto. Similar dedication may one day turn up a body that so far lives only in theory. Stars, rather than growing and diminishing in brightness, seem to switch abruptly on and off. First discovered in the late 1960s, these so-called pulsars emit regular, very rapid bursts of radio wave energy, typically about once per second, but in the case of a millisecond pulsar, once every few thousandths of a second. While theorists were quick to develop an explanation for the slower paced variety, they have been hard-pressed to account for the dizzying rate of millisecond pulsars. Pulsars in general are believed to be neutron stars, the tiny, incredibly dense remnants of supernova. When a dying star explodes into a supernova, the momentum of its original rotation is concentrated in the surviving inner core, which begins to spin rapidly, emitting radio waves along its magnetic axis. The rhythmic blinking of a pulsar occurs only if the magnetic axis lies perpendicular to the axis of rotation and is aligned so that the beams of radiation strike Earth. But what makes a millisecond pulsar spin so fast? The likeliest conjecture is that matter from a companion star, pulled by the neutron star's intense gravity, spirals down onto it, adding momentum and increasing the pulsar's rotation rate. Yet in some cases, millisecond pulsars have been found without a partner. In March 1988, however, Princeton astronomers detected a millisecond pulsar with a curious hiccup in its rhythm that may hold the key to the puzzle. Every 9 hours, the pulsar's rapid fire beat disappears for 50 minutes. Because the interruption is clearly too long to be caused merely by the passage of an eclipsing companion, astronomers believe that a swathe of matter evaporated from the surface of such a companion is blocking the signal, blown off by the intense radiation from the pulsar. The vaporized star stuff forms a broad tail that spreads into interstellar space. After a few billion years, this so-called black widow pulsar will completely destroy its mate, a white dwarf so small and dim it at first escaped detection, and will then join the ranks of solo millisecond pulsars that were once inexplicable. A flashing plasma searchlight. Over the course of a year, a number of stars will blaze up like cosmic flashbulbs in the sky. These phenomena, known as novae, occur in close binary systems where the greater gravity of one star draws matter from its less substantial companion. As the matter accretes onto the surface of the more massive star, temperature and pressure increase until finally they trigger nuclear fusion, which usually happens only in stellar cores. Incandescent matter is blasted into space and the star brightens by a factor of many millions. As a result, one recent nova provided both a public show and an astronomical puzzle. Nova Cygni 1975 burst into view in the year of its name with such brilliance that it could be seen even in the night skies of light-drenched cities. Like all novae, it began to fade quickly. concentrating the build-up of pressure and temperature that would ultimately set off the nova blast on a small portion of the dwarf's surface. When the explosion occurred, the same magnetic forces channeled bubbles of the hottest and densest material out from the polar region. Rotating with the star, the jet of plasma pulses produced a radiant spot on the envelope of matter, blasted away from the star. Then, as the envelope contracted of its own gravity, the pole remained the most luminous region, flashing like a circle